Can we trust published papers that use statistics? No, and I will show you what it takes to make valid regression analysis using my new poster. Welcome to Marcharts. To understand why we cannot use statistical reporting from papers to judge validity of studies, we need to first understand what statistics does. Take this example. A census of 10-year-old children in a country showed a mean height of 136.1 centimeters with a standard deviation of 6.4 centimeters. Now, 10 years later, because say the country was torn apart by a war, you suspect that this average height decreased. But you cannot perform a census, the war just ended. So you take a random sample of 15 children and find out that the sample mean is just 133.07 centimeters. It is less as expected, but is this enough evidence to claim that the height really decreased? So what we do here is that we assume that nothing changed. The mean and the standard deviation are the same, and we simulate how the sample mean of a randomly selected sample of 15 children from this theoretical population is distributed. Because the population was normally distributed, it does not matter how big the sample size is. The resulting distribution is normal. But it has 15 times smaller variance, which comes from our sample size. Now, this distribution gives us probabilities of observing certain sample means. You can notice that the curve is thickest around 136.1 centimeters, because if that is the actual population mean, your sample mean will be likely within 2 standard deviations from this number. But it is possible, only unlikely, that you will get much more extreme sample means several times the standard deviation away. So how likely is our observation of 133.07 centimeters? That does not quite make sense to ask. You can watch this video to find out why. But we can ask what is the probability of observing this or a more extreme sample mean. This is determined by the area under the curve. The whole area is 1, and this bit, extending to tiny probabilities in infinity, is finite 0.033. This is pretty small, and most statisticians would say there is enough evidence to say that something with our assumptions is wrong. They then would end up concluding that the population mean indeed decreased. There are 2 issues with this. First, maybe nothing is wrong. It is well possible that we make such an extreme observation, especially if we actually did not believe that the population mean decreased beforehand. Maybe we just explored many hypotheses, look at the weight or different age categories, and thus tested maybe 100 different hypotheses. Probability of 0.033 means that 3 out of 100 times we would make such an extreme observation. And we would then try to find some rational justification and publish the result, but this is not how statistics should be done, and why you should not easily trust the statistical reports. Hold on a second, are you saying that this is how researchers publish their results? Well, this is called p-hacking, and many perhaps don't do it intentionally. Maybe they don't understand how statistics works. And reviewers cannot tell them because these things are usually not mentioned in papers. This is precisely where the current open science drive can help. The future actually looks promising. Second, coming back to the statistically significant result, maybe something else is wrong with our assumptions. It does not have to be the population mean that has changed. Maybe the standard deviation changed, or the population is not actually normally distributed, or our sample was not randomly selected. Statistical significance only means that something very likely went wrong, but it does not say what it is. Now, this is very important to realize when we interpret results of ordinary least square regression. Say that we wish to explain how education influences wage. For that, we need to include relevant variables such as gender and age, because those may be correlated with education, but also correct the exponential nature of wages and parabolic influence of age on wage. Otherwise, we would try to capture nonlinear relationship with a linear model. The ordinary least square method is one possible way how to estimate the slope coefficients and the intercept in our linear model using data. Geometrically, it picks those coefficients as our estimators that give us a point in the linear space defined by our model that has the closest squared Euclidean distance to the complex wage data after the logarithmic transformation. The underlying idea is to interpret complex real-world data with a simple abstract model that we can understand. Now, we can test the hypothesis whether the estimated coefficients for education is different from 0. Using simulated data, these coefficients of 0.18 means that if education increases by 1, wage increases by 19.7%. This is a slightly more complicated interpretation of the coefficients than usually due to a more complex functional form. The probability of obtaining this or a more extreme coefficient is 0.037, given the assumption that this coefficient was actually 0. Before we would claim that the education is relevant for wage, should we use real data? It is important to realize that, as before, this is not the only assumption that can be wrong and would explain unlikeliness of our observation. In fact, there are a lot more assumptions that can go wrong in linear regression than in the simple statistical test from the beginning of the video. For example, one assumption is that there is no heteroscedasticity. The error variance is constant. However, we should never test hypotheses if this assumption is violated, even if we use a very large sample. Okay, there is a test to detect heteroscedasticity called the Bruce-Pagan F-test for heteroscedasticity. So we use it. The idea is that if the error variance is constant, we should not be able to explain squares of the residuals obtained from the initial model. In other words, if the F statistics is significant, the assumption that all regression coefficients except the intercept are 0 is likely wrong, and we need to correct heteroscedasticity in the original estimation. Except that we run into exactly the same issue as before. This is not the only assumption that can be wrong. In fact, we need all the restrictive assumptions of regression analysis in place if we want to interpret F statistics. How do we then know what is wrong? We do not. In fact, using my simulated data, the Bruce-Pagan F-test detected heteroscedasticity, while the model was in fact misspecified. Well, maybe this should be a misspecification test then. No, I have made another simulation where the model was still misspecified, but the test did not come out significant. Contrary to what has been historically done, neither significant F statistics nor a high R-squared carry any information about the validity of a regression model. Max Planck once said that science advances one funeral at a time. People used F statistics and R-squared because it was their teachers who developed the concepts, because they saw these numbers programmed into software. The new generation will see things differently. So how do we make a valid regression analysis? First, we try to assume as little as possible. No independent normality of errors, rather collect a large sample size to random sampling and collect heteroscedasticity by Eicher-Huber-White robust estimator. Do not test whether it's present, just correct it every single time. This is not the most efficient way to deal with heteroscedasticity. There is generalized least square regression. But you know what? Just correct it, because who cares about efficiency if validity is in question? I work as a journal editor, and we receive many papers doing regression analysis. I have never seen anyone correcting heteroscedasticity. Not a single time. I guess it is because the R software does not do it automatically. What you need to do is to load library sandwich and type $VCOVHC to learn how to do the correction. But even more important for getting a valid regression analysis is using theory and common sense to include omitted relevant variables that are correlated with other explanatory variables, correctly specify the function form of dependent and explanatory variables, and avoid endogeneity. Endogeneity is the unpleasant role in regression analysis. It throws his club into your results so you get the nonsense. For example, if you try to evaluate the effectiveness of a training program in increasing wage, you run into a problem that both making the choice to attend such a program and low income are correlated. To address this, you would need to make an experiment where you assign people to the training program randomly. Another issue is two-way causality. Naturally, increased demand provides incentive for suppliers to increase the supply. But it is also the availability of supply that drives the demand. For example, policymakers would not require people to get insurance if the insurance industry was not already developed in the country. Since making an experiment is not possible, you would need to employ instrumental variables and the two-stage least square regression. Omitted variables, wrong specification, and endogeneity are big problems that no sample size and no statistical test can solve. What is worse, you cannot even recognize these problems by looking at statistical reports. To be convinced that a paper performed a valid regression analysis, authors need to show you a lot of theory, use common sense, and employ right instruments to get the correct model. And here you have it, ordinary least square regression in one math chart. Best wishes from our charts!